Hello, I'm Tirthankar from BSMS Physics third year, and I'm here to present my project on parameter learning for differential equations using physics-informed neural networks for the course Fundamentals of AI/ML PhD 351. So, first of all, what are differential equations and why deep learning is necessary for learning and training on differential equations is because uh, differential equations we know are very useful, are very needed to model complex systems. They are descriptive of real life systems, and to know and predict the solutions of those partial or ordinary differential equations and be able to model them is very useful. Deep neural networks are very recently been utilized to tackle this problem of finding and the solution and modeling these complex systems, and they have been very successful. We will see later. And the reason this is very important to be able to use ML for predicting the solutions of PDs is because standard numerical approaches like finite difference method or other methods are very difficult to be practically used because PDs have very complex solutions, sometimes significant nonlinearities, shocks, and other reasons, and it takes huge amount of computational resources to actually model a system up to significant time. Now, deep learning has emerged as a new way to do this because of their universal approximation and also great expressivity and be able to learn complex solutions. They are very promising in this area because they can learn the evolution of the system and predict what will happen once they are trained. Neural networks, in particular, among all of the machine learning and deep learning methods, have proven to actually learn the underlying behavior, the relations, nonlinear, complex relations of the inputs and outputs that describe the systems. Physics-informed neural networks are a specific class of deep learning or neural network methods that have been used and are being used to solve problems involving PDEs. They they are different from generic neural networks is that pins like neural networks are trained by approximating the loss function by reducing the loss function. But the loss function of a physics-informed neural network involves residuals of the partial differential equation. Basically, what it means is that from the image shown that the loss function includes terms that help the uh, neural network learn solutions that actually satisfy the equation. The derivative loss terms are included as well as the generic boundary or initial or data loss terms. And this helps a lot in the evolution or the learning of, of the neural networks. Now, pins like neural networks, of course, are deep learning networks that, given an input in the integration, the spatiotemporal domain, produce an output by learning the solution implicitly. And this incorporation of the PD residuals is the novel approach that is used in physics-informed neural networks and has been shown to be much, much effective. So that is part of the reason why pins are used. But there are more reasons why pins should be considered. Because, like first of all, as I already told, physics-informed neural networks consider the partial differential equations. They take that into effect. They don't just fit the solution that is best description of the data, but they also make sure that the solution learned actually satisfy the physics or the equations that govern the system. And most importantly, physics-informed neural networks are mesh-free methods. Reason this mesh free is important is because for standard numerical algorithms to evolve or to learn or to simulate the system, you have to make a mesh grid. And the finer the mesh grid, the better the solution you will be able to learn, or the better the simulation will be. But as the mesh grid resolution increases, computational resources required increases by a lot, by orders of magnitude. But pins being mesh free do not have this problem. They can learn or simulate bigger systems or at a more minute details, even without any huge requirements. Once they're trained, you can like find the solution for a later amount of time or for a small de- different kind of initial condition or something just by inference. And this is very, very fast. And also, what is important is that the way pins is made is that you can also solve inverse problems. Inverse problem means that most often we solve problems like for the differential equation, we give a set of parameters for it, and we want the networks or neural networks to learn the solution. But pins give the advantage that they can be used to learn the parameters that give rise to the solution for these PDs. This is very important because sometimes we know the behavior of a system, but we don't know how what set of parameters give rise to that. Like, so for example, if we know like how an airplane behaves in a specific weather, we can know the way the air is working, the air is affecting the airplane by inverse in the calculations. This can be done because pins like neural networks incorporate auto differentiation, which can be used to go move to inverse problems as well. And forward, of course, they can solve easily as well. And as also mentioned, they can address PDs in very complicated geometries, high dimensions. This is all difficult for Newman algorithms because computational resources increase orders of magnitude to solve these kinds of problems when the geometries or dimensions become very high. Now, for the parameter learning part that was in the title, parameters, as I said, are the constants or the quantities that define the solution the PDE gives. For the same amount, the same PDE, different solutions exist. Different kinds of initial boundary or other conditions can give rise to different solutions. This is a natural property of differential equations. That's why they don't have a unique solution. And this parameter learning is very essential for PDs because for some systems such as fluid mechanics systems or convection systems, the parameters hugely change the solution. As you can see from the image, this is the ground truth solutions using numerical techniques of various convection equations with an initial condition 1 plus sin x and reaction equations initial condition of Gaussian. As you can see, the solutions vary, even visually they vary by a lot when the parameters are just changed. A simple change of parameters can change the solutions by a lot, even to the point when sometimes you cannot even figure out that the same different set of solutions are from the same PD. And this parameter learning is important because for many systems, you know the equations, but you don't know like which kind of conditions or parameters are there. So, like the inverse problems I mentioned, this if it's a system, something knows like for the same PDE, different parameters can be rise to like it has the knowledge the system can help us in figuring out what kind of parameters give rise to a specific solution we are interested in. And physics-informed neural networks for up to now have been used for surrogate modeling and like in general learning the solutions of differential equations, but they have been used like for a single solution, learning of a single solution. Like given a set of parameters and a different PDE, train the PMs and see how well they can learn the solution, the underlying physics, and the equations that govern the system. But this is usually not useful because in real life simulations, you need a system that can learn the dependence of parameters and the solutions given the PDs, because or else the numerical algorithms that have been developed are being developed for decades. So if a competitor needs to have some sort of edge, only computational efficiency is not good enough. For this to show that whatever we have done in our work on parameter learning, we are using this system. The system is a non-gravitating isothermal hydrodynamic system. This system is chosen because of various reasons that is mentioned. But first, the governing equations are this. The first equation is the mass conservation. The second equation is the momentum conservation. These equations define the system. As you can see, they are partial differential equations, and they are couple partial differential equations actually, which makes the learning even more complex. Isothermal isothermal system is chosen because with isothermal system for linear, there are cases basically, linear and non-linear. In linear case, the waves, this system is basically waves traveling in mediums, like what's happening when a wave moves. So for linear cases, the wave behaves like a simple wave. It does not do any changes to the system. It just is a traveling wave behavior. You can see a traveling wave behavior. And with nonlinear, this is important. With nonlinear, we can see shocks being formed. Shocks are like say, regions of very high density or very high velocity movement, and these are like places where the evolution, the change of density and velocity is also very, very rapid. Now, neural networks have been able to show good performance with learning differential equations generally. But for these kinds of systems where there is like different kinds of behavior for different values, or there are very non-linear evolution like shocks being formed or a collapse is happening somewhere, these are very hard even for neural networks to learn because they are using the gradient descent, and gradient descent is finding the best solution that can fit the PDE, not the best solution that actually describes the system. Pins have shown better results, but simple vanilla pins have also struggled with learning nonlinear evolution. But our work, I'll show what my work has been able to do with this system as well. The architecture we used has been inspired by the work on parameter informed pins. It's a P-square pins. The reference paper is attached at the end. The core of our architecture, the main thing that differentiates us from simple vanilla pins, is the use of a three-layer architecture. Basically, if you see in the image, there are two subnetworks, small networks, and there is a big network at the right. One of the small networks takes the parameters that define the solution and the relation of the solution and the differential equations. And the second, the below small network at the below takes the spatial and temporal coordinates. These networks use the uh, inputs they are given and produce hidden representations. And the hidden representations are then concatenated and then passed to a final denominator, and the whole system is trained by uh, minimizing the PD residuals, the PD partial differential equation loss, the boundary loss, and the initial condition loss. The boundary and initial condition losses are required because for a specific solution to a PD, you need to define the initial and boundary conditions. The losses are minimized and the solutions are found. And the main thing we are doing is this three-layered architecture. The parameter that is being taken for our system is the perturbation strength parameter, the rho 1A that is mentioned in the image. This is the part of the model implementation, some of the main code snippets. The parameter embedding network takes the learnable parameter, which is referred to as alpha in the code and rho 1A in the previous image, and produce the hidden representation as we mentioned. And the input embedding network takes the spatial and temporal coordinates. And the final pin class on the pin network takes the hidden representations, concatenate them, and then produce the final solutions. The major one and the two major implementations that we have used to better find better solutions or have better performance are the sinusoidal activation functions. If you can see for the input embedding and the main pin class, we have used the sign activation function. This sign activation function helps in learning high frequency solutions. What I mean is that for some systems, the if you look at the Fourier basis, the solution is dependent on some high frequency uh, like high frequency modes. So using a sign activation or a smooth activation, sign or cos, we use sign, but cos have also shown similar results from other papers. So these kind of smooth activation functions are very useful, are very good in helping the networks learn such high frequency solutions. And what is not shown here but have been done in the code is a residual connection. Now, residual skip connections, we use residual version, are uh, have been shown to uh, improve training stability and help the model converge better. It also helps in passing information through the network because what happens is for very deep networks, the information that is available to the initial hidden layers is sometimes is not passed to the later hidden layers, and this like results in a break of information passage. So these residual connections help in passing the information. For our case, it's not shown here, but in the code there is. We take the hidden representation of the first layer of the main pin network and uh, concatenate add it with the uh, output input of the fourth hidden layer. So the fourth hidden layer outputs gets the information from the initial what the initial hidden layer is getting as well as the information that has been passed on to the network. This is only done for pin class because the hidden and embedding networks takes simple inputs, so they do not need very deep networks, and hence there is not much requirement of a residual connection. And this is the main part. The main defining feature of pins is the modification to the generic loss function that is used in neural networks. As you can see from the small code snippets attached, the PD residue function is the function that helps in finding out the PD residuals associated with a solution found by the model. And this is combined with the IC and the BC law, boundary condition, and the initial condition loss to get the final loss that is been minimized by a model. As it already been mentioned by me before, initial and boundary conditions need to be defined to find a unique solution to a PD. And the reason also why initial and boundary condition losses are important to be minimized, the network has to learn to minimize them, is because for different initial and boundary conditions, the solutions of the partial differential equations involve change. As I've seen from a previous image for the convection equations, the same even though parameters also change the equation, but initial conditions also do change. We use 1 plus sin x in one of the previous images, 1 plus sin x is used, but changing it changes the solutions. And the pin must know what initial conditions are there. It must learn to respect the initial conditions and the boundary conditions. What is not shown here, but is also with the code is very big, so I could not attach everything. Is that weights are also associated with the initial boundary condition and partial differential equation losses. The optimal values for the weights are found is in trial and error for many learn after many runs. These weights are important because sometimes the model tends to focus more on reducing the PD loss or sometimes the IC loss, and finding a balance is important, or else the model will learn to respect only one set of conditions and not the other. And this also helps in converging to better solutions, which is kind of intuitive because if the pin respects the IC, the boundary conditions, and the PD at the same time, then the solutions will naturally be close to ground truth solutions. So for the results part, this is the first set of results we have. This is the first case with linear perturbations, the initial perturbations for the linear. Linear case is being defined here as any perturbation strength that is less than zero point 0.1. For this case, we have trained the model with 10 uniformly spaced uh, rho 1a or alpha values, the perturbation strengths, which is the parameter that is used to change the solution of the equations between zero point 0.1 and zero point 0.5, and the test results for 0.02 and 0.04 are here. And the error metric that is used, the epsilon that you can see, or relative misfit, is the weighted average, weighted relative error between the PNN solution and the final difference of the two solutions. These are the continuation of the results for a nonlinear case. The nonlinear case is basically any perturbation strength greater than zero point 0.1. This has been the model has been trained for 10 uniformly spaced values within zero point 0.1 and zero point 0.5, and then tested for values zero point 0.2 and zero point 0.4. The error metric used is the same one as before. So some notes and the interpretation of the results. For linear perturbations, the model has very good loss, very good convergence. The error is consistently below 5%. For nonlinear cases, the error, as you can see, is close to 10% for some regions. But because with nonlinear cases, the shocks being to develop in the system, as I seen before, shock formation happens in our system, and this is tough for neural networks or even pins to learn. So 10% the error rises because of that, because shock to learn shocks is not easy for neural networks or pins in general. But we can see that the model qualitatively, or it has been able to learn the behavior of the system, what the evolution of the density and velocity should be. And one thing we have also done is training the model and testing it for extrapolation in temporal domain, mainly because the temporal evolution is the main hard part to learn for neural networks. These models, as you can see, have been tested for time up to 2.5, but the models have been trained up to time to 2 only. And we can see that the model is able to follow the evolution of the system. For linear cases, it has been very successful in following the evolution of the system, even beyond the point up to which is trained. And some notes about the results. The comparisons from linear theory are done for linear perturbations only, because for only linear perturbations there are analytic solutions that can be derived by using linear theory, and the finite difference solutions are done using the Lax method. This has been done for both linear and nonlinear cases because Lax method or finite difference methods can be used for both cases. And for both of the case, linear and nonlinear, the model is trained using a combination of 1001 Adam iterations and 201 LV FGS iterations. This combination of using Adam first and LV FGS later has been shown in multiple cases to improve convergence, because the when Adam is used first, it traverses the lost landscape very fast and finds good and decent solution, and then LVFGS can be used to further find the better global minima if everything goes ideally, or a good local minima in the lost landscape. And for both cases, 2000 initial condition points, 2000 boundary condition points, and 20,000 collocation points domain was used. Then the training was done in two batches of 10,000 points. About the batches, I'll show. what it means. This is a part of the additional features that have been implemented. The first, which is a very important one, is batch processing. Batch processing is very important to allow training on neural networks with limited resources. I had limited resources, so GPU resources specifically. So implementing batch processing have helped me a lot in being able to train these systems with uh, with my personal resources. And it has also been shown, but not true for our system, but has been shown that with batch processing, the convergence is typically faster and the models usually don't tend to overfit. And one or two other things that have been implemented are some partial support for training 2D and 3D systems. Our systems that have been trained and tested on our own, only 1D systems, but some of the functions have been defined for 2D and 3D. In the future, based on this course or systems can use this core 2D and 3D functions to further train models for 2D and 3D systems. Of course, for 2D and 3D, you will need much bigger networks or much complex uh, methods like domain decomposition or causal training or other systems. And one more thing, we have used a non-gravitational system. Gravity is not included, but hydrodynamics usually involves gravity, and gravity, although including gravity does not results in shock, but it results in collapse. And being able to learn collapse will be a very good way to show the in general ability of pins in learning complex partial differential equations. All of our course in a modular course structure. So for easy running, training, and testing. And these are some of the additional features that can be used for any future. And that's all. Thank you for listening.